Hey guys, in this video we'll be going over the code for the Lidar add-on. We'll first be going over the general idea of how a Lidar sensor works. Then we'll be covering a simple program where we read the distance from our Lidar sensor. And finally we'll cover an application program where we move our bot based on the distance values read from our Lidar sensor. So let's first go over the general idea of how a Lidar works. A Lidar, or a time-of-flight sensor, is used to find the distance between it and the nearest obstacle in front of it. Now, a Lidar is made up of a laser and a photosensitive sensor. So what it does is first, the laser will emit a beam of infrared light. This beam will travel from the Lidar to the nearest obstacle in front of it. It will reflect off that and go back towards the Lidar. Then the photosensitive sensor on the Lidar is able to detect when the beam has hit the Lidar. Now the Lidar is also able to calculate the amount of time it took for the beam to travel to the obstacle and back. Since we now know the time it took, and we also know the speed the beam travels at, which is of course the speed of light, we're able to multiply the speed and the time together to get the distance. However, we also have to divide this value by 2, as the time that we measure is accounting for the beam traveling towards the obstacle and back from the obstacle. But with this, we are able to calculate the distance between the Lidar and the nearest obstacle in front of it. So now that we understand how a Lidar is able to actually calculate distance, let's go over a simple program which can show how we can read this distance from our sensor. So here's the program. For this program, we're using this header for the specific library, which we use for the specific sensor that we're using, the VL53L0X. Then here we define our distance sensor object, and we also define the 2 pins that we'll be using to communicate with the sensor. In this case, we're using pins 21 and 22, which are connected on the stacker to the connectors on the back. Now this sensor specifically uses an I2C interface, and the connectors on the back of the stacker are designated for any sensors like these that use this interface. We also declare these 2 variables, which we'll go over later, and they'll deal with the timing of our loop. In setup, the first thing we do is we set up our serial monitor, and this will sort of act like how a terminal would in certain program IDEs, and essentially it will allow us to communicate with our Arduino. Then we set the pins that we'll be using to communicate with the sensor. And this piece of code will initialize the sensor, and we see that we use this print line function. And what this does is that it will simply print something in our serial monitor. So if we're able to connect to our sensor, it will print distance sensor initialized. Now moving on to the main loop, essentially what we want to do with this program is read the distance from our sensor and print it out in the serial monitor. So first thing we will do though, however, is we don't want to necessarily print the distance out for every iteration of the loop. That will flood our serial monitor with values. So what we're going to do is we're going to have the distance be read only every 100 milliseconds. To do this, we use this millis function, and this will essentially it'll act like a timer, and it'll store the time since the Arduino has last been reset, and we'll store it in this variable current time. And this is where we use those two variables from earlier, last measure time and measure interval. And what this if statement will do is if the current time minus the last measured time, which by default is 0, is greater than 100 milliseconds, meaning that at least 100 milliseconds have passed, then we'll execute the rest of our loop. First thing we do, of course, is reset the last measured time to the current time to keep it updated and make sure that, again, we go through the program every 100 milliseconds. Next, here we declare this measure structure, and what this will be used, it comes from our library, and it's used to store different values which represent relevant information from when the sensor performs a distance measurement. Now, to actually do that, we can use this ranging test method, and then this will allow us to get the distance from our sensor. So going back to this measure structure, the two important values that we'll be taking from it is range status and range millimeter. Range status stores an integer where each integer means a specific thing. The important ones for us is 0 means that an accurate value has been measured, and more importantly, 4 means that the first obstacle in front of the sensor must have been out of range. So if range status is equal to 4, then we know that whatever's in front of the sensor is out of its range. And the other one is range millimeter. This just stores the distance that the sensor reads in millimeters. So we say if the range status doesn't equal 4, so that means that the first obstacle is in range, then we'll print distance, and we'll print the distance that we read, again, using this range millimeter value. And then, of course, if the obstacle is out of range, then we'll simply print that in our serial monitor. So now let's see our program in action. Currently, I have a Stackr with the Lidar add-on connected to my computer. And if I open the serial monitor, we can see that it's printing the distance that it reads. So I'm going to hold my hand out in front of it, and as I move my hand closer towards it, we see that the distance that it reads gets smaller. If I move my hand away from it, the distance that it reads gets larger, of course, because I'm moving my hand away from it. So we see that the sensor is pretty accurately able to read the distance of the nearest obstacle from the sensor. Of course, there is chance for slight variation, but for our purposes, it is accurate enough. Now let's go over this application program, which is meant to be used with the Stackr and the Lidar add-on. Now, what the program is meant to do is it should move our Stackr right in front of the first obstacle in front of it. If it's too far away, then the Stackr should move towards the obstacle, and if it's too close, it should move backwards, away from it. Now let's go through the program. We see actually that the program is quite similar to the one we covered previously. However, it also, of course, has the logic necessary to tell what the motors to do, and of course the setup for the motors. Hence the two libraries, and of course the definition of the pins that are connected to the motors, and the declaration of our motor objects. Here we declare a distance sensor object and the two pins we're using to communicate to the sensor. Here, these are the two variables we used in our last program that help us determine when 100 milliseconds has passed, when each interval has passed, and thus when to read from our distance sensor. Again, we don't want to read necessarily every iteration of the loop. The setup is exactly the same. We still set up our serial monitor in case we want to debug. Here we initialize the distance sensor. And now we get to our main loop. The beginning of our main loop is, again, the same as the previous program. We're just making it so that we only read from our distance sensor every 100 milliseconds. And just to clarify, it is important that we use this millis function and we don't simply just delay, because if we delay, that's going to stop everything, including our motors, from moving. Then here, this is just performing the distance measurement like we covered earlier. We use that ranging test function. And here we store the distance that we read in this variable distance. Now we get to the actual code that tells what the motors to do. So if the distance is greater than 100 millimeters, then we tell both motors to start spinning forward, to move our stacker forward. If the distance is less than 60 millimeters, then we tell both motors to start spinning backwards. And if the distance is not either greater than 100 or lower than 60, so it's within that 60 to 100 range, then we simply tell both motors to stop spinning. Now, of course, if the obstacle, whatever it may be, is out of range, because in our previous if statement we made sure that range status didn't equal 4. So if it is out of range, then we'll simply print that and we'll just tell both motors to start spinning forward anyways. So now let's test out this program. Here I have a Stackr with the Lidar add-on and the program loaded onto the microcontroller. So if I turn the Stackr on and hold my hand out in front of it, currently the hand is at the 60 to 100 meters range. If I move it away, the Stackr will move towards it. If I move it closer, then the Stackr will move away. So we can see that the Stackr is able to roughly follow my hand. That concludes our lesson on programming the Lidar add-on. Thanks for watching.